just for the. Okay, so just a refresher. The mathematical analysis that we're learning now will allow us, beginning with mass or percent composition given, be able to determine the formula of a compound, which is really powerful information. So we talked about, we're first going to learn how to find the empirical formula. And we call the empirical formula the simplest. But what do we mean by that, Caitlin? What did you pick up from yesterday? What is the difference between an empirical and a molecular formula?
Like the subscripts are like as low as they can go. They can't simplify any further.
Perfect. So for example, N2O5, empirical or molecular?
Empirical.
Perfect. We could not simplify the two subscripts by the same factor and get whole numbers from there. But something like N3O9, I totally made that up because it doesn't exist, but this would be interpreted to be a molecular formula. You could reduce these both by a factor of 3 and then get NO3. These are different compounds, so even though you can multiply this 3 times to get that, or divide out by 3 to get that, a different formula is a different compound with different properties. Okay, so we were working our way through and giving an example of Anna discovering a new compound, and she is trying to find its identity, starting with percent element mass data. So we said if there's kind of a series of steps, and really, we'll just think through these. I would never encourage you to memorize these. And once we've gone through the third example, it'll just be second nature. So usually we start with percent by mass of each element. And we said the first thing we're going to do is assume we have 100 grams of sample. And max, what does that do for us? If we, oh, go ahead. I'm sorry, sir. Go ahead.
That means that whatever the percent is, that's how many grams are.
Perfect. And really, when I said it will make our numbers really cooperative, that means we just write, instead of a percent, G. So you're not moving the decimal place to the right or to the left. And we can often make mistakes when we do that. So you don't have to start the problem writing percent of each element. You can begin by writing the mass of each element. Okay? So assume 100 grams of sample, and then we write percent as gram of each element. Yes, ma'am?
Will it ever not be 100 gram sample?
You can choose whatever mass you want. You can choose whatever mass. So if you have a favorite number, you can say, okay, I'm going to pretend that I have 55.5 grams. Well, then to get the mass of each element, we have to calculate. So what is 36.5% of 55.5 grams? So you'll have to do an extra math step, but you can. So if we make the assumption we have 100 grams, well, 36.5% of 100 is 36.5. So we're just making our numbers. We are choosing that because that will lead to the least mistakes. Okay. All right. So then we said, well, the goal is we know our compound is made of these elements, but what is the formula? What is the ratio of atoms? Well, we said, okay, if we just say we have 100 grams of sample, then percent can be written as grams. But a formula is not mass relationships. So this is where we ended. We said we need to convert grams to moles. All right, so that's where we are. So, Ella. Remember, Elena did the conclusive thinking for us to say, okay, if we use the example of carbon dioxide, if we have 1 mole of CO2, That does not mean, because we have a ratio of 1 carbon to 2 oxygen, that we have 1 gram of carbon for every 2 grams of oxygen. Subscripts are not masses, but we can interpret them to be moles. If we have 1 mole of compound, then we'd have 1 mole of carbon and 2 moles of oxygen. Okay. What do we use, Ella, to go from grams to moles?
I don't remember, but I think it's atoms.
Okay. So what would you do to convert out of grams and get into moles? Can we do that? So you said atoms. Well, if I don't want grams, and remember we can put that over 1 if we want. I want to put grams in the denominator, and then do we know a relationship between grams and moles of an element?
I remember doing this, I just don't remember exactly. I don't think I can go through that.
All right. You want to phone a friend?
Yeah.
And if we had all the answers, I don't think we'd be need to take chemistry. So please don't worry. Please don't worry. We haven't done this for a little while. Phone a friend.
Is it Avogadro's?
Okay. Avogadro's number. Do you remember? It's okay if we don't. We haven't used it for a while.
No, I don't remember.
That's okay. And you remember any, Oscar.
Is it 6.22 something?
It's 6.022.
Times 10 to the 23rd.
That is the number of things in 1 mole of that thing, just like 12 in a dozen. Well, if I have 1 mole of this compound, it will be then Avogadro's number. Now, this is made of sodium. I don't know the subscripts yet. I'm just going to call them X, Y, and Z, if you don't mind. Okay, Megan, what kind of a compound is this? Ionic, covalent, and acid? So $5,000 question of the day. If we have 1 mole of ionic compounds, we'd have Avogadro's number of what? What's the smallest piece of an ionic compound? Abby?
An ion?
Not too shabby. An ion is an ion so if you had a castle made of Legos that have the 2 circle things on top and they're all blue, a whole castle, well, the smallest piece of that would be a Lego with 2, right? Not part of a Lego. Ionic compounds are made of ions, plural. So what would 1 ionic compound be? 2 words. Excellent. So Abby, very good. Leah, very good. A formula unit. If it's covalent, what term do we use? Smallest piece of covalent. Molecule. Yeah, that's supposed to be an M. Sorry. Molecule. Yes, yes, yes. Now, it depends, Abby, because if you would have, we know that ionic compounds are made of cations and anions, and we don't know the ratio yet. So we might have 1 sodium ion for every whatever this combination is. Okay. Formula units. Okay. I don't see grams. So Elena, I'm so glad you reminded us of that. So we're not trying to get formula units into it or out of it, or atoms. We're dealing with grams and moles. You guys know, why did I say get a periodic table? We're going to need the numbers. What numbers? Yes. What did you say? A little bit more. Atomic mass, if we look at sodium, the atomic mass would be, oh, Dewey, I'm trying to, would be 23. We'd round that to the whole number. We only use atomic mass or mass number when we're trying to get protons, neutrons, electrons. So what do we call it when we round it to the 100th? Phone a friend if you need.
Is it average atomic mass?
Average atomic mass. It's a weighted average. Is it all coming back? Hopefully. Okay. So for sodium, there are 22.99 grams in every 1 mole. Max, sir, what number do we use for sulfur? And Ty, could you get us the average atomic mass of oxygen? All right, no. All right, yesterday, my 5th period class for their percent of oxygen and potassium chlorate. For the mass of oxygen, I told them it will not be 48. If anyone writes 48 grams, there's a consequence. And I asked them what the consequence would be. And they came up with, we have to come to the room during our lunch. We still get to eat our lunch, and we help you with a chore in the lab. So I know, because Max, I think we need to have a consequence if I call on you and you're clearly not paying attention.
I have the answer though.
I think that's a whole lot of bull. What did I ask you for?
The answer to.
No,
Oh.
no, I didn't. I asked you for the average atomic mass of sulfur.
Oh, I thought.
No.
Oh, okay, well, it's 32.0, and if we're going to hundreds, 0.6.
No. Oh, shoot. Is that crazy that we have different numbers on different periodic tables? According to that, it'd be 0.06. I apologize. If we take a look at the periodic table that I give you on tests and so on, look at that. That would round to 0.07. Forgive me for saying no so firmly. You choose, Max. Do you want to go with 0.06 because that's what you gave?
Yeah.
Okay. And Ty, what about oxygen?
15.99. Or should I round to 16.00?
What do you think?
Round to 16.
Okay, is it okay? I'm always puzzled when I get asked, should I round? Isn't it always a possibility? If you want to carry your value further than the 100th, but minimally we need to the 100th. Okay, so do you want to round to the 100th?
Sure.
Okay, so
16.00.
yeah. All right. Now, Max, can you give us what the answer would be here in moles of sulfur? And then, Avi, could you please get moles of sodium? Alina, could you please get moles of oxygen? I'd appreciate that. Go, sir.
I got 0.7923. Wait, but I thought we went, isn't it bullshit? Oh wait, so the lowest is 25.4.
So,
It's the lead, I thought, oh wait, the trailing's the one you don't count. So I forget these.
okay. Zeros can be tricky. This is a captive zero between two non-zeros we count as significant. But a leading zero never counts as significant. Trailing will count if there is a decimal. So these count as sig figs. This counts as a sig fig. That does not count as a sig fig.
So then it should be 0.792, right?
Yes.
Yeah.
Okay, sodium, please.
0.792. Oh, sodium.
Thank you.
That was wrong. I gave you something.
Oh,
1.59.
and oxygen, please.
6.38.
Excellent. All right. Now, just as I just said, okay, what we are after is our formula. Percent, can't do anything with it. Grams, a little bit better, but moles. Now, we're almost there. What this is saying is you have this many moles of sodium for this many moles of sulfur and this many moles of oxygen. But we write whole numbers as subscripts, not decimal values. So what we do is this. The next step is you divide each mole amount by the smallest mole value. Okay, we divide each mole amount by the smallest mole value. And what that is doing is it is forcing our smallest value to be 1. Okay, mathematically, that's why we do that. So you do not have to rewrite these. I'm going to rewrite them just because I'm trying to identify step by step by step. So we just found that we have 1.59 moles of sodium. We have 0.792 moles of sulfur and 2.38 moles of oxygen. So we take our smallest value, which, Tyler, is
0.792.
and we're going to say, okay, I'm going to force this to be 1. So I'm going to divide this by 0.792. So in essence, what we are saying is, okay, if we have 1 mole of sulfur, then how many moles of sodium will it be? And how many moles of oxygen will it be? All right, Austin, can you divide 1.59 by 0.792 and tell us what we got? Maddie, would you mind taking 2.38 divided by 0.792?
Sorry.
That's okay. I love you guys dearly. We need to tighten up a little bit of our behaviors because when I said we need a calculator, dude, sounds a little bit of a walk of shame.
Uh, 2.012.
Sig figs.
2.01.
Yes. Now, if it's a problem that I've given you, so not lab numbers, so tomorrow, not necessarily going to be as cooperative, but if you follow the steps correctly, when we divide by the smallest value, you are going to get whole numbers, and we can easily round these to a whole number. So they may vary, maybe within 500ths. That's it. So if you have 2.05 all the way to 1.95, we can round that to 2. We're either going to get whole numbers in a half, whole numbers in a third, or whole numbers in 2/3. And we'll do all the examples. We're not going to ever have 1 1/4 or 1 3/4. Hello. Thank you. All right. Abby, this is for the end of the period for you, okay? So what this means is, dun, 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 we have 2 sodiums for every 1 sulfur for every 3 oxygens. And I know, Ella, can you name that compound?
Would that be nitrate or nitrate? No, wait. Sodium. Sorry. Sodium. I was like going for a loop.
I know, that's okay, because you were just seeing if to make us laugh.
Yeah. Sodium
Sol items.
Yes, which sadly, Anna, we know of, not a brand new discovery. Very sorry. But that would be it. Yes,
How do we know what order to put them in?
phenomenal question. What about this? How do we know what order? When we write a formula, Oscar?
Like if it's ionic, the non-metal or like metal would be first and then the non-metal.
Perfect. So if we have a metal, we know that's going to be our cation. The overwhelming majority of the time, it will be the order in which you're given elements in the problem. Yeah, and we'll do enough examples that you'll see this. That's a great question. Yes, ma'am.
Will you ever like have to round it? Like if you got 3.5, would you round it up to 4?
No, we're going to do an example of what to do.
Okay.
Okay, so we have to pause here. We could get whole numbers and a half, so you're 3.5, or whole numbers and a third, and whole numbers and 2/3. So we'll do an example of that next. Okay, so if we're looking at, sure, I'm not sure exactly where I put it. So again, not to memorize, we assume we have 100 grams. So we start by writing grams. We need to get to moles and then divide all mole values by smallest amount of moles. And then possibly adjust the subscripts, but find subscripts if we want steps. All right, so can we do an example that don't get whole numbers? So what if, really good one for us. We are going to say that let's see, Ella did a lab and she reacted 8.65 grams of iron with 3.72 grams of oxygen. Now, you don't have to turn to it because I want to keep us on this example. This is an example beyond your packet. The overwhelming majority of the time, our givens are percent by mass of our elements. Sometimes we start with the mass of the elements, but usually it's percentage because that's what the instrumentation will tell us. Sometimes we go right to the second step. Okay, so Abby, if we have mass of each element, what would we do first? Perfect. Remember, Ty found for us that oxygen is 16 grams and iron, Anna, what is the average atomic mass of iron, please?
55.85.
Excellent. Yeah. Okay, so when we do our math, okay, judging to correct sig figs, of course. And we would get 0.155 moles of iron and 0.232. All right, Sam, what do we do now? So we have moles of each element.
Okay, I have no idea what.
That's okay. That's okay.
You divide it by the small.
And your smallest is?
Iron.
Yes. I'm sorry that I needed you to repeat that. So dividing that by 0.155, dividing this by 0.155, we of course get 1. Now, I want to show us if it's a problem I've given us. We may be above or below a whole number and a half, a whole number and a third, or 2/3 by just 5/100ths. But look, with rounding here, we are right on 1.5. Okay, now, what this kind of tells us is our formula is Fe1O 1.5, and that's ridiculous. If we ever get non-whole numbers, that is telling us that our formula doesn't have a subscript of 1. And not all formulas do. Not all formulas do. So we just have to think, so what multiple do I try that then will deliver whole numbers for iron and oxygen, but still an empirical formula? Avi,
Fe2O3.
why?
Multiplied by 2 is just one whole.
If we just double. Okay, so what this is telling us is we don't have a subscript of 1. So let's multiply all of them by 2. And great, we end up getting 2 for Fe and then 3 for oxygen. And it's still an empirical formula, isn't it? There we go. Let's just say that our answers were 1, let's say, mole of iron, and then 1 1/3. What would that look like as a decimal? Excellent. And I'll just go to the 100th because that's what our math told us. Okay. So we know, so we don't have a subscript of 1. Multiply by 2, will that resolve it? No. Ella, what should I multiply by?
3.
Yes. If I multiply by 3, then I get Fe3O 4. Yeah. You guys know, I mean, fractions, bleh. But if we want to see 1 1/3, if we multiply 1 1/3 by 3, right? 3 and 1, so 4. All right, the other possibility. What if we got 1 mole of iron, but then 1 2/3? What would that look like as a decimal? 6/6. Yeah. Multiply by 2.
Multiply by 4.
Yeah. If we multiply by 4, we'll get 4 and then 8
No,
thirds?
that's wrong.
Okay, not bad, not bad.
No, you multiply by 3.
Multiply by 3. And then we'll get Fe3O 5. Yeah. Okay, those are our possibilities. Okay, so ladies and gentlemen, on page 25 in your packet.
Will this be on the quiz tomorrow?
I'm sorry?
Will this be on the quiz tomorrow?
No, it will not. Thank you for asking. Thank you for asking. And I was going to address that in just a second. All right. Sam, choose one of these 1 through 7.
1, 2.
Oh, thank you. I was hoping for 2. Can we do 2 can we also do 7? And one more. Leah, can you choose one that I have not circled?
4.
4. Sounds wonderful. Okay, yes, ma'am.
Can you repeat what page it is?
I'm sorry?
What page is it?
Oh, 25. Page 25. I apologize. Page 25. Can we please do these 3 empirical formula? We're having a second take, if you will, or, another go at our naming and formula writing. Nothing different except different names and formulas. It'll be another 20. You'll have 20 minutes. We'll go over our homework. Then we'll proceed onward with part 2 of our tin and oxygen creation compound lab. Questions as we end? So I've added several supportive tabs within Canvas module 7. There's a couple like digital reviews if you want to take 5 or 10 minutes, and it's a combination of everything. Yes,
Do
ma'am.
you have another copy of that packet that you gave us before? Like, I already did it, but can I have like another copy?
Oh, I sure do.
Okay.
I sure do. And so this, remember, this was a practice that we did. That's what Elena is talking about. Yeah, definitely. You're welcome. Sure. Oh my goodness, yeah. Remember, there was like a whole set of extra practice. Yeah. And if you're reviewing and you have any concerns for me, you can always email. Okay. Any concerns as we end? All right, I wish you a great rest of your Tuesday.